Hey everyone, and welcome. If you're one of Mr. Chi's students or you follow him online, you are in exactly the right place. Today, we're going to tear down a classic grade 12 electrochemistry question. So if redox reactions have been giving you a hard time, stick around. We're going to get this sorted. All right, let's just jump right in. These electrochemistry questions, especially a big one like question 8, they can look super intimidating when you first see them on an exam. But trust me, there's a logic to it. Once you see the pattern, it all starts to click. We're just going to walk through it piece by piece. No stress. So first up, we've got question 8.1. This part kicks off with a pretty common scenario, a metal reacting with an acid. This is one of those core concepts, so let's make sure we have it completely locked down. Here it is, the reaction they give us. We've got solid magnesium mixing with hydrochloric acid, and it's making magnesium chloride and hydrogen gas. The first task? Prove that this is a redox reaction. So, where do we even begin? Well, we start right here with the basic definition. Redox is all about one thing: electrons moving from one place to another. So if we can just show that one substance is losing electrons, that's oxidation, and another substance is gaining those electrons, that's reduction, then boom, case closed. And the absolute best way to track those electrons is by using oxidation numbers. And this little table lays it all out perfectly. First, let's look at magnesium. On the left, it's just a pure element, so its oxidation number is 0. Easy. But on the right, in the product, it's become a +2 ion. It's number 1 up, which means it must have lost negative electrons. That, my friends, is oxidation. Now, check out hydrogen. It starts at +1 in the acid, but it ends up as H2 gas, which is an element, so its number is back to 0. Its number went down, meaning it gained an electron. That's reduction. Since we've got both happening, we've officially proven it's a redox reaction. Awesome. So the next part of the question, 8.1.2, asks a classic follow-up. Which one is the oxidizing agent? Now just remember the simple rule for agents. They're named for what they cause, not for what happens to them. Exactly. The oxidizing agent is the substance that causes oxidation. And how does it do that? By taking electrons for itself. In other words, by getting reduced. In our reaction, the hydrogen ion, the H+, is the one that gained electrons. It got reduced. And in doing so, it caused the magnesium to lose its electrons. So, H+, or if you want to be thorough, the HCl, is our oxidizing agent. All right, let's keep this momentum going. For the next couple of questions, we need to grab our data sheets. The table of standard reduction potentials. Seriously, that table is your absolute best friend in any electrochemistry problem. Let's see how to use it. So now the exam gives us a new piece of information. They tell us, hey, if you drop a piece of copper into hydrochloric acid, nothing happens. Crickets. Our job is to explain why. And the answer is all about comparing strengths. If you look at that trusty table of yours, you'll see that copper, Cu, is listed as a weaker reducing agent than hydrogen gas, H2. For a reaction like this to happen, the metal has to be a stronger reducing agent. It has to be better at giving away electrons than H2 is. But copper? It just isn't. It can't force its electrons onto the H+ ions. Magnesium, on the other hand, it's way higher up the list, a much stronger reducing agent, which is why it bubbled away like crazy. Okay, this is a great little curveball. Question 8.1.4 asks, what about a different acid? What if we try nitric acid with that copper? It seems like a similar setup, but there's a really important difference hiding inside that formula. And the answer is a big yes. It will react. And here's why. With nitric acid, the H+ ion isn't the main character anymore. The real powerhouse, the secret weapon, is the nitrate ion, NO3-. Go look at your data table again. You'll see that the nitrate ion is a way, way stronger oxidizing agent than H+ is. It's so powerful that it can actually rip electrons away from the copper atoms, forcing a reaction to happen where the weaker hydrochloric acid failed. Okay, time to switch gears completely for the second half of the problem, question 8.2. We're moving away from simple reactions in a beaker and stepping into the world of a galvanic cell. You might also know it as a voltaic cell. So the question gives us this line of symbols here. This is called cell notation, and you can think of it as a super condensed blueprint for the entire galvanic cell. Our first job is to take this blueprint and translate it into a full, balanced net ionic equation.
Let's just break it down into 4 simple steps. Step 1, identify the anode half reaction. That's always on the left. So we've got lead getting oxidized and releasing 2 electrons. Step 2, the cathode half reaction. On the right, we see iron 3 gaining 1 electron to become iron 2. Now for the most important part, step 3, you have to balance the electrons. The anode is giving away 2, but the cathode is only taking 1. That won't work, so we multiply that whole cathode reaction by 2. And finally, step 4, just add the 2 half reactions together. The electrons on both sides will cancel out, and you're left with your net equation.
And there you have it, the final, perfectly balanced answer. 1 solid lead plus 2 iron 3 ions gives you 1 lead 2 ion and 2 iron 2 ions. Done.
We're on the home stretch now. The very last part, 8.2.2, is a quick thinking question. It asks, what if we took out the lead and swapped it with an even stronger reducing agent? What would happen to the initial voltage of the cell, the EMF?
The answer is simple. It increases. Just think about it this way. The EMF, or voltage, is basically the push that's shoving the electrons through the wire from one side to the other. A stronger reducing agent is way more desperate to get rid of its electrons. It gives them a much harder push. This bigger push creates a bigger potential difference between the 2 sides, which we measure as a higher initial EMF. So let's just take a breath and recap. By tackling this one single exam question, we've actually built up a whole set of essential skills. Think of this as your personal redox toolkit that you can use on any problem they throw at you. Just think about everything we did. We assigned oxidation numbers to prove a reaction type. We identified the key players, the oxidizing and reducing agents. We learned how to use our datasheet to predict whether a reaction will even happen. We translated that weird cell notation into a proper chemical equation, and we even figured out how to predict changes in a cell's voltage. These 5 skills right here, they're the whole game. Look, I know chemistry can feel overwhelming sometimes, but remember, getting good at this isn't about some flash of genius. It's just about doing these small things like working through one problem at a time over and over again. You keep putting in that daily effort, and I promise you, you will see the results. And hey, if this breakdown helped things click for you, then you absolutely have to make sure you're following Mr. Chi on TikTok and subscribe to his YouTube channel. He's always posting more tips, practice questions, and full explainers just like this to help you kill it on your exams. And that is a wrap on question 8. I really hope you're feeling a bit more confident about this stuff now. To keep the ball rolling, I've got a question for you. Drop a comment below. What's the one chemistry topic, big or small, that you want to see us break down next? Let us know. Keep up the amazing work, and we'll catch you in the next one.